Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University Gwalior. Today we are going to discuss about a module solution reactions under paper fundamentals of analytical chemistry. When a chemical reaction is carried out in a closed vessel, the system achieves equilibrium. And the law of mass action states that the rate of a chemical reaction is proportional to the concentration of the reacting substances. The molecule breaks down into ions upon addition of solvent or energy in the form of heat, and ionization takes place. Ions can be separated from the solution through the fractional precipitation on the basis of their solubilities. Solution reactions. What are solution reactions? Many of the reactions of qualitative and quantitative interest, or when qualitative and quantitative chemical analysis takes place in a solution, the solvent is most commonly water, but other liquids may also be used. A solution consists of two or more substances dissolved in a liquid form. Not to get confused with a mixture which is heterogeneous, multiple substances exist in varying structures. Solutions are homogeneous, which means that atoms of solute are evenly dispersed throughout the solvent, which may be water or ethanol. So there is a clear-cut distinction between a solution and a mixture. It should not be confused. It is one is homogeneous solution, whereas mixture is heterogeneous solution. In solution, solute is distributed homogeneously in a solvent and it forms a true solution. Chemical equilibrium is the state in which both reactants and products are present in concentrations which have no further tendency to change with time. As you can see in figure 1, that rate of forward reaction and rate of backward reaction, and they are meeting at a time when they are meeting at this point, it is the reaction is at equilibrium state. It is found that after the elapse of a sufficient time interval, all reversible reactions reach a state of chemical equilibrium. In this state, the composition of the equilibrium mixture remains constant, provided that the temperature also remains constant. In the equilibrium state, the two opposite the two opposing reactions are taking place at the same rate so that the system is in a state of dynamic equilibrium. If a mixture of hydrogen and iodine vapor is heated to a temperature of about 450 degrees centigrade in a closed vessel, the two elements combine and hydrogen iodide is formed. It is found, however, that no matter how long the duration of the experiment, some hydrogen and iodide remains uncombined. If pure hydrogen iodide is heated in a closed vessel to a temperature of about 450 degrees centigrade, the substance decomposes to form hydrogen and iodine. But again, no matter how prolonged heating is, some hydrogen iodide remains unchanged. This is an example of a reversible reaction in the gaseous phase, that hydrogen molecule in gaseous phase plus iodine molecule in gaseous phase, they form hydrogen, two molecules of hydrogen iodide in gaseous phase as shown in the following equation. Chemical equilibrium state results when the forward reaction proceeds at the same rate as the reverse reaction. The reaction rates of the forward and backward reactions are generally not zero but equal. Thus, there are no net changes in the concentrations of the reactants and products. Such a state is known as dynamic equilibrium. It is found that after the elapse of sufficient time interval, all reversible reactions reach a state of chemical equilibrium. In this state, the composition of the equilibrium mixture remains constant provided that the temperature also remains constant. There are some factors under which the composition of the equilibrium system is maintained. Temperature. If the temperature of an equilibrium mixture of nitrogen, hydrogen, and ammonia is increased, then the reaction which absorbs heat will be favored and so ammonia is decomposed. Pressure. If the pressure of the system is doubled, thus halving the total volume, the two sides of the equation are equally affected and so the composition of the equilibrium mixture remains unchanged. Concentration of the component. If hydrogen is added to the equilibrium mixture resulting from the thermal decomposition of hydrogen iodide, it is found that more hydrogen iodide is present when equilibrium is restored. The law of mass action. Law of mass action is the principle that states that the rate of a chemical reaction is proportional to the concentration of the reacting substances. Active mass was interpreted as concentration and expressed in moles per liter by applying the law to homogeneous systems, that is, to systems in which all reactants are present in one phase. Consider first the simple reversible reaction at constant temperature A plus B forming C plus D. The rate of conversion of A and B is proportional to their concentrations, or if we take R dash is equal to K1 into in bracket A into B in bracket, where K1 is the rate constant or rate coefficient. Similarly, the rate of conversion of C and D is given by R2 is equal to K2 into C in bracket into D in bracket. At equilibrium, the two rates of conversion will be equal, that is R1 is equal to R2 or K1 into A and B both in bracket is equal to K2 into C and D both in bracket. So on combining or solving equations, K1 upon K2 is equal to C into D upon AB is equal to K capital as shown in the above equation. K capital is the equilibrium constant of the reaction at a given temperature. The expression may be generalized for a reversible reaction and may be represented as given in the following equation, where P1, P2, P3 and Q1, Q2 and Q3 are the stoichiometric coefficients of the reacting species. Now, there are various factors which affect chemical reactions in solutions. These are three main factors whose influence on chemical reactions in solutions are to be considered and is very important. First factor is the nature of the solvent, then temperature, and finally the presence of catalysts. The nature of the solvent. It is convenient to classify solvents as ionizing solvents if they tend to produce solutions in which the solute is ionized, and as non-ionic solvents if they give solutions in which the solute is not ionized. Temperature. Reaction rates increase rapidly with rising temperature, and in some analytical procedures, it is necessary to heat the solution to ensure that the required reaction takes place with sufficient rapidity. The presence of catalyst. The rates of some reactions can be greatly increased by the presence of a catalyst. This is a substance that alters the rate of a reaction without itself undergoing any net change. In electrolytic or ionic dissociation, the addition of a solvent or of energy in the form of heat causes molecules or crystals of the substance to break up into the ionic into electrically charged particles as shown in figure 2. Degree of dissociation alpha depends on electrolyte concentration and usually decreases with increase in concentration. As you can see in this figure, how Electrolytic dissociation is taking place when we are applying energy, when we are adding some form of other solvent. These substances are being ionized. The strong electrolytes are immediately ionized, whereas weak electrolytes are not completely ionized. Aqueous solutions of many salts of the common strong acids and base, such as are good conductors of electricity. The above solutes are therefore termed electrolytes. Certain solutes, for example, ethane 1,2-diol, which show a conducting capability only little different from that of water, such solutes are referred to as non-electrolytes. Salts. The structure of numerous salts in the solid state has been investigated by means of X-rays and by other methods. They are composed of charged atoms or groups of atoms held together in a crystal lattice. They are said to be ionic compounds. When salt is dissolved in a solvent of high dielectric constant, such as water, it undergoes limited ionization and following equation exists Ba in equilibrium with B plus A minus. Acids and bases, when dissolved in water, undergoes dissociation with the formation of hydrogen ions as the only positive ions. Whereas bases are defined as substance when dissolved in water undergo dissociation with the formation of hydroxide ions, OH minus ions as the only negative ion. As shown in the following equation, NaOH gives Na plus OH minus. What is activity? An activity coefficient is a factor used in thermodynamics to account for deviations from ideal behavior in a mixture of chemical substances. Activity is a measure of the effective concentration of a species under non-ideal conditions. This determines the real chemical potential for a real solution rather than an ideal one. Activity is equal to concentration into activity coefficient. Solubility product. A substance's solubility product Ksp is the mathematical product of its dissolved ion concentrations raised to the power of their stoichiometric coefficient. Solubility products are relevant when a sparingly soluble ionic compound releases into solutions as shown in figure 3. A solubility product is a specific form and equilibrium constant. Solubility product changes with temperature. AB will form ions, A plus ions and B minus ions, and the KSAB is equal to A plus into B minus in bracket. Fractional precipitation is a technique that separates ions from solution based on their different solubilities. It can be used to determine which ions are present in a solution by taking advantage of their solubilities. A mixture of metal ions in a solution can be separated by precipitation with anions. Figure given below, that is the figure 4, show it represents the fractional precipitation of proteins. Here it has been shown how fractional precipitation of proteins take place. It has been illustrated in this figure. Effects of acids on the solubility product. For sparingly soluble salts of a strong acid, the effect of the addition of an acid will be similar to that of any other indifferent electrolyte. But if the sparingly soluble salt Ma is the salt of a weak acid Ha, then acids will in general have a solvent effect upon it. If the dissociation constant of the acid Ha is very small, the anion anion will be removed from the solution to form the undissociated acid Ha. Consequently, more of the salt will pass into solution to replace the anions removed in this way, and this process will continue until equilibrium is established. The solubility of the precipitates encountered in quantitative analysis increases with rise of temperature. With some substances, the influence of temperature is small, but with others, it is quite appreciable. In many instances, the common ion effect reduces the solubility to do so. A small value, that temperature effect, which is otherwise appreciable, becomes very small. Wherever possible, it is advantageous to filter while the solution is hot. The rate of filtration is increased, as is also the solubility of foreign substances, thus rendering their removal from the precipitates more complete. Acid-base equilibria in water. Consider the dissociation of a weak electrolyte such as acetic acid in dilute aqueous solutions. So here, acetic acid in water will form H3O plus and acetate ion negative available. This will be written for simplicity in conventional manner. CH3COH is equal to H plus CH3COO minus. The H plus represents the hydrated hydrogen ion. Applying the laws of mass action, we have acetate ion in bracket plus into proton ion in bracket upon acetic acid is equal to K capital A. K is the equilibrium constant at a particular temperature and is usually known as the ionization constant or dissociation constant. Strengths of acids and bases. The Bronsted-Lowry expression for acid-base equilibria A1 plus B2 is equal to A2 plus B1 leads upon application of the law of mass action to the expression K is equal to A2 in bracket B1 in bracket upon A1 in bracket in B2 in bracket, where the constant K depends on the temperature and the nature of the solvent. Another very important in solution is very important thing to understand in solution studies is common ion effect. The concentration of a particular ion in an ionic reaction can be increased by the addition of a compound which produces that ion upon dissociation. The particular ion is thus derived from the compound already in solution and also from the added reagent, hence the name common ion. Goldross and Heidwiller in 1894 found that the most highly purified water that can be obtained possesses a small but definite conductivity. Water must be therefore be slightly ionized in accordance with the equation H2O in equilibrium with H plus plus OH minus. Pure water is very weak electrolyte and ionizes according to the above equation. Since water is only slightly ionized, the ionic concentrations will be small and their activity coefficients may be regarded as unity. The activity of the unionized water molecules may also be taken as unity. Ionic product of water. Applying law of mass action to equilibrium, the value of dissociation constant K comes to as K is equal to H plus into OH minus upon H2O, all entities in the bracket. Since dissociation takes place to a very small extent, the concentration of undissociated water molecules may be regarded as constant. Thus, the product H2O gives another constant which is regarded as Kw. H plus in bracket OH minus in bracket is equal to Kw. This constant Kw is termed as the ionic product of water. A common kind of hydrolysis occurs when a salt of a weak acid or weak base is dissolved in water. It spontaneously ionizes into hydroxide anions and hydronium cations. The salt also dissociates into its constituent anions and cations. For example, sodium acetate dissociates in water into sodium and acetate ions. Buffer solutions. The resistance of a solution to changes in hydrogen ion concentration upon the addition of a small amounts of acid or alkalinity is termed as buffer action. A solution which possesses such properties is known as buffer solution. It is said to possess reserve acidity and reserve alkalinity. Buffer solutions usually consist of solutions containing a mixture of a weak acid and its sodium or potassium salt, or of a weak base B and its salt. A buffer then is usually a mixture of an acid and its conjugate base. Complex ion. The increase in solubility of a precipitate upon the addition of excess of the precipitating agent is frequently due to the formation of a complex ion. A complex ion is formed by the union of a simple ion with either other ions of opposite charges or with neutral molecules. The stability of complex ions varies within very wide limit. It is quantitatively expressed by means of stability constant. The more stable the complex, the greater is the stability constant. That is, the smaller is the tendency of the complex ion to dissociate into its constituent ions. The application of complex ion formation in chemical reactions depends upon the fact that one component may be transformed into a complex ion which no longer reacts with a given reagent, whereas another component does react. Complexation. The process of complex ion formation can be described by the general term complexation. A complexation reaction with a metal ion involves the replacement of one or more of the coordinated solvent molecules by other nucleophilic groups. The groups bound to the central ion are called ligands. Here, the ligand can be either a neutral molecule or a charged ion, and successive replacement of water molecules by other ligand groups can occur. Ligands may be conventionally classified on the basis of the number of points of attachment to the metal ion. The simple ligands, the simple ligands such as halide ions or the molecules H2O or ammonia are monodentate. That is, the ligand is bound to the metal ion at only one point by the donation of a lone pair of electrons to the metal. Metal ion buffer. A metal ion buffer provides a controlled source of free metal ions in a manner similar to the regulation of hydrogen ion concentration by a pH buffer. A metal ion buffer solution contains the free metal ion along with a complex compound formed by the association of the ion with the ligand in excess. The concentration of free metal ion depends on the total concentration of each component, that is, ligand and metal ion, as well as on the stability constant of the complex. Electrode potential. When a metal is immersed in a solution containing its own ions, say zinc in zinc sulfate solution, a potential difference is established between the metal and the solution. The potential difference E for an electrode reaction is given by M having number of electrons. Mn plus means electron deficient. It will take n number of electrons and will convert it into M ions, or M ions will eject number of electrons and will be in the ionic form. M n plus means one or two or three electrons has been ejected from it, and it is represented by the equation E is equal to E0 plus RT upon NF in equilibration with the log of activity of Mn plus. For measurements of electrode potential, three electrode system is as shown in following figure is used. Next is concentration cells. An electrode potential varies with the concentration of the ions in the solution. Hence, two electrodes of the same metal but immersed in solution containing different concentrations of its ions may form a cell. Such a cell is termed as a concentration cell. The EMF of the cell will be algebraical difference of the two potentials. If a salt bridge be inserted to eliminate the liquid junction potential, oxidation reduction cells. Reduction is accompanied by a gain of electrons and oxidation by a loss of electrons. In a system containing both an oxidizing agent and its reduction product, there will be an equilibrium between them and, and electrons. That is, electrons will move from one side to the other side. When they are in equilibrium, where electrons will move from one side to another side. If an inert electrode, such as platinum, is placed in a redox system, for example, one containing iron 3 and iron 2 ions, it will assume a definite potential indicative of the position of the equilibrium. Many of the reactions of qualitative and quantitative chemical analysis take place in solution. The solvent is mostly water, but other liquids may also be used. Chemical equilibrium is the state in which both reactants and products are present in concentration which have no further tendency to change with time. The composition of the equilibrium mixture remains constant provided that the temperature, and for some gaseous reactions the pressure also remains constant. So students, today in this module we have studied how by taking different types of different types of salts which are ionized when putting in water, different types of terminology. We have studied what is equilibrium, how equilibrium is attained, how reaction takes place. All things we have studied in this module. Thank you.